All right, let's talk about something you've probably seen 1,000 times, but maybe never really thought about. You know those giant metal towers marching across the countryside with wires humming in the air? Well, have you ever wondered why those lines are carrying such ridiculously high voltage?
I mean, it sounds kind of nuts, doesn't it? We generate all this power, then we crank it up to these super dangerous levels to send it across the country, just to bring it all the way back down again so you can plug in your toaster. What on earth is the point of all that?
Okay, so to figure this puzzle out, we need to understand that every good story needs a villain. And in the story of electricity's long journey to your home, the villain isn't what you might think. It's this invisible force that's constantly trying to steal our energy.
Yep, the bad guy here is just heat. Think about how your phone or your laptop gets warm when it's working hard. Power lines do the exact same thing, but when you're talking about a wire that's hundreds of miles long, that little bit of warmth turns into a massive amount of lost, totally wasted energy.
So let's get into it. Where is all this energy-sucking heat actually coming from? Well, to find out, we have to zoom in and look at what's happening right inside the wires themselves, and this right here is the key to everything.
Now, there's a fancy scientific name for it, joule heating. But forget the jargon. Just think of it like this. No wire is a perfect superhighway for electricity. Every wire has a tiny bit of what we call resistance, which is basically electrical friction. And just like when you rub your hands together, that friction creates heat. And all that heat, that's just lost power. Energy that was generated but never, ever gets to you.
And what's really cool is that the engineers who figured this all out didn't have to just guess. Nope, they used some pretty straightforward physics to pinpoint the exact culprit behind all this waste.
Okay, don't let the formula scare you. It's actually super simple. It says the power we lose, P loss, is equal to I squared times R. Now, R is that resistance, that electrical friction we talked about. We're kind of stuck with that unless we make our power lines out of solid gold or something, so that leaves I, the current. That's our guy. That's the real troublemaker.
But here is the absolute game changer. It's not just I, it's I squared. That little 2 makes all the difference. It means that if you double the current, you don't get double the heat loss. You get 4 times the loss. If you triple the current, you get 9 times the loss. This is huge. It means current isn't just a problem, it's an exponentially bad problem. We absolutely have to get the current as low as humanly possible.
So that's the big question, right? The multi-billion-dollar puzzle. How do you deliver a ton of power, which is what a city needs, but use a tiny little bit of current to avoid that insane heat loss? It feels impossible. Like, how do you do both at once?
Well, this leads us to one of the most elegant and honestly kind of counterintuitive solutions in all of engineering. It turns out you can have it both ways. You just have to trade the current for something else.
And here's the other half of the magic. Another simple formula. The total power delivered equals voltage times current. Now remember, this P is the good stuff. This is the power we actually want to use to light up our homes, not the P loss we're trying to get rid of.
So here it is, the brilliant trick. Think of voltage and current on a seesaw. The total power delivered is the plank they're balancing on. If you want to keep that plank perfectly level, but you push the voltage side way up into the sky, what has to happen on the other end? Yep, the current side has to go way, way down to keep it all balanced.
So, let's put it all together. Step 1. Right at the power station, you crank the voltage up to insane levels. Step 2. Because of that seesaw effect, the current absolutely plummets. Step 3. Since our enemy, heat loss, is based on that current squared, then now teeny tiny current means the heat loss practically disappears. Boom. Problem solved.
Okay, so that's the why, but what about the how? I mean, you can't just turn a giant voltage knob, right? So what's the actual piece of technology that pulls off this amazing trick?
The unsung heroes of our entire electrical grid are these things called transformers. You've got these massive step-up transformers at the power plant that do the cranking up. Then, all the way at the other end, in those little substations in your neighborhood, you have step-down transformers that do the exact opposite. They bring the voltage all the way back down to a safe, usable 120 or 240 volts.
So look, if you forget everything else, just remember this one thing. This is the whole shebang right here. We use super high voltage because high voltage equals low current, and low current means we barely lose any energy as heat. That's it. That's the secret. And it's such a beautiful, elegant solution to a really tricky physics problem. It's happening all around you right now completely silently, and it's pretty much the invisible backbone of our entire modern world.
I mean, this system is over 100 years old.
And it's absolutely brilliant. It works so well. But it does make you think, right? As we look towards the future, to renewables, to totally different ways of making and using power, what's going to be the next brilliant solution?